afternoon and welcome back. We've reached the end of our unit on functions, and to finish it up, we're going to learn about inverse functions. To find the inverse of a function, and we denote that with f with this superscript of -1. Please make a note that this is not an exponent. And we don't treat it as an exponent. This is a notation. So just like we've seen in previous lectures that similar symbols have different meanings based on their context, here we have another one. So to find the inverse of a function or any equation, you're going to start by switching x and y. Just straight up flip them around. And then you're going to solve for y. Once you get y by itself, that will be your inverse. Okay, so let's try this. We have f of x equals x squared plus y, or x squared plus 9. We know that f of x is the same thing as y, so this is just like saying y equals x squared plus 9. And our first step is to switch our x and y values. So y becomes x, and x becomes y. And now we want to take this equation in red and solve for y. We want to get y by itself. Subtract 9 from both sides. X minus 9 equals y squared. And to get y by itself, we're going to take the square root of both sides, remembering that when we take the square root, we have to add plus or minus. So our inverse is equal to plus or minus the square root of x minus 9. Let's try another one. F of x equals negative 3x minus 4 divided by x minus 2. I'm going to jump into that first step where I switch x and y. This y is going to become x, and every x is going to become y. Negative 3y minus 4 divided by y minus 2. Now we need to solve for y. We've got 2 of them, so we're thinking in our head, eventually we need to get all of those y's together. We're going to clear the denominator first by multiplying both sides by y minus 2. And on the left-hand side, we're going to go ahead and distribute that x. So we have xy minus 2x is equal to negative 3y minus 4. As I mentioned previously, we want to get all of our y's together, and then we really want everything else to the other side. So to start combining our y's on one side, I'm going to add 3y to both sides. And so that I've got only y's on the left-hand side, I'm going to add my 2x to both sides. So now I've got xy plus 3y is equal to 2x minus 4. If I look at this left-hand side, both of my terms have a factor of y. So I can factor it out, and my other factor is x plus 3 equals 2x minus 4. And now we can see that isolating y only requires dividing both sides by x plus 3. And we now have our inverse, which is 2x minus 4 divided by x plus 3. To verify that two functions are inverses, if I have f of g of x equals x or g of f of x equals x, then I know that f of x and g of x are inverses. Recognize these statements. We're talking about the composite function. If you take the composite function of f and g and you get x when you simplify, that tells me that f of x and g of x are inverses. Now, it is true that it doesn't matter how you create your composite function. If you keep f on the outside, g on the inside, or you switch them, if f of x and g of x are in fact inverses, it will always simplify to x. So it's not essential that you find both f of g of x and g of f of x. We'll just find one. So given f of x equals 3 minus 2x and g of x equals negative 1/2 x minus 3, let's find the composite function to determine if f of x and g of x are inverses. Now I chose f of g of x simply because it's first. And remember, we're going to start by writing this in function notation so that I can see what I need to substitute. So g of x is the same as negative 1/2 times x minus 3. This whole thing is what I'm going to substitute in for x in f of x. So f of x was 3 minus 2 times this whole expression, negative 1/2 times x minus 3. Now I've used brackets and parentheses just so that you can see the different groupings, but brackets are the same thing as parentheses, and they're just indicating that I'm multiplying negative 2 times this. So we have 3 minus, if I multiply from left to right, negative 2 times negative 1/2 is positive 1. So we have negative 2 times negative 1/2 is positive 1 times x minus 3. And distributing that 1, we have 3 plus x minus 3. Combining like terms, we get x. So our composite function f of g of x is x. Therefore, that's what those 3 dots mean if you've ever seen them in a text. Those 3 dots in a triangle mean therefore. Therefore, f of x and g of x are inverses. Now we could have gone through the process of finding our inverse functions, but this is a technique that you're going to be assessed on. So make sure that you guys are comfortable with finding the composite function and understanding what does it mean when we get a composite function of x. Now if I know that f of x and g of x, two completely random functions, if I know that they're inverses, it tells me something very special about the domain and range of each of them. If f and g are inverses, then the domain of f is the same as the range of g. The range of f is the same as the domain of g. Now this concept comes into play when we're trying to find the domain and range of certain functions. We've seen that finding the domain of a function algebraically is quite easy. If we have a rational function, we're looking for the zeros of the denominator. If we have a square root function, we're setting our argument greater than or equal to 0. But finding the range is far trickier unless we have a graph. But we don't always have a graph to look at. So using our inverse functions and the relationship between inverse functions, if I wanted to find the range of a function f, I really only need to find the domain of its inverse. This idea is so important. Let's make sure we bedazzle it a little bit. When we get to our last unit on exponential and logarithmic functions, we're going to come back to this concept. Horizontal line test. You remember the vertical line test. We use the vertical line test to determine if a graph is a function. The horizontal line test we use to determine if the inverse is going to be a function. And it's the same tool. If any horizontal line intersects the graph more than once, then the inverse will not be a function. A one-to-one function, sometimes written as 1-1, is a function whose inverse is also a function. This should say is. Now let's think about that for just a second. We've talked about the definition of a function. Every input has exactly one output. So now we've got a new type of classification for a function, a one-to-one function. This is defined as a function whose inverse is also a function. How do I know if a graph represents a function? Well, it has to pass the vertical line test. So we know that whatever we're referring to passes the vertical line test. But this function also has an inverse that is a function. How do I know if the inverse is going to be a function? That's our horizontal line test. So if I have the graph of a function, I can determine if it's one-to-one by applying both the vertical and the horizontal line tests. So let's look at some examples. In our first graph, the one up top, is this going to be one-to-one? It is a function, it passes the vertical line test, but does it pass the horizontal line test? If I draw a horizontal line there, it intersects this graph twice, which means that it is not one-to-one, and that also implies that the inverse is not a function. If the inverse is not a function, thinking about the graph, that means that the graph of the inverse is going to fail the vertical line test. And we're going to talk about the graphs of inverses in just a minute. If I look at my second graph, this graph in the lower left-hand corner, it passes my vertical line test. All of these are examples of functions. Does it pass my horizontal line test? When I draw a horizontal line here, it only intersects once. Students always question this bottom piece though. You can see this yellow line getting closer and closer to that x-axis. And in fact, it continues to approach the x-axis, but it never touches it. And so it never actually becomes horizontal. So this does in fact pass the horizontal line test, which means that it is one-to-one, which implies that the inverse is a function. And looking at our last graph, it is a function, and it will also pass the horizontal line test. So this is also one-to-one. Whose inverse is a function. As I mentioned in our last unit, we'll be talking more about inverse functions. Our last unit is on exponential and logarithmic functions. And these two graphs in the bottom represent those two families of functions. This one on the lower left is an exponential function. The one on the right is a logarithmic function, and these are actually inverses of each other. So something to remember, because we will see that again down in Unit 5. Let's talk about the graphs of inverse functions. The graphs of inverse functions are reflections about the line y equals x. That's our identity equation. It's that diagonal line that has a slope of 1 that goes through the origin. So if I'm looking at this graph, it looks like half of a parabola. I'm going to sketch on this the line y equals x. that goes through. The origin has a slope of 1. Looks like this. Now you guys can't do this, or I can't do this, but you guys can. Take your paper and just turn it so that this diagonal line looks vertical. And when you see this line being vertical, it makes it much easier to reflect that graph about it. But when we do that, a good sketch is going to look something like this. That graph in red is an approximate reflection about that line. Now, this is simply a sketch, just to get the idea that we're reflecting about that line y equals x. In this next example, we're going to talk about how to get the exact ordered pairs for our inverse. And that goes back to how we found the inverse of an equation. What was our first step when we were trying to find the inverse of an equation or a function? It was to switch our x and our y values. Then we went on to learn about the relationship between domain and range of inverse functions. Remember that they were switched. So if I have a function like I have here, and I want to graph its inverse, all I'm going to do is take the ordered pairs and switch their x and y values. So again, to find the points of the inverse, you're going to switch the x and the y values in the ordered pairs of your original function. So to practice that, let's look at this graph. And this represents f of x. So this is our original. We're going to graph its inverse. So let's label this. This is f of x. And looking at our ordered pairs, let's label them. This point down here is -3, -3. This point is -2, 2. And this point up here is 3, 4. I'm going to graph my inverse in red. Starting up here, if I've got a point 3, 4 on my original function, I'm going to have the point 4, 3 on the inverse. That cut off just a little bit. That's the ordered pair 4, 3. If I have the point -2, 2 on my original function, I'm going to have the point 2, -2 on the inverse. 2, -2 is down here. And if -3, -3 is on my original function, switching those ordered pairs doesn't change the point, so that point will also be on my inverse. And if I connect these points, and I envision that line y equals x that goes along that diagonal, we can even see the reflection of that graph about that line. Graph f of x equals x squared plus 1 for x values greater than or equal to 0 and its inverse. Graphing this function doesn't seem like anything special, but there is this one extra piece here that maybe we want to talk about for x values greater than or equal to 0. Why do you think that I'm restricting the domain for f of x when the domain is all real numbers? Well, let's think about what the graph of f of x is going to look like. Since we have that x squared, we're thinking it's going to look like a parabola. So visualize that parabola. Now, if I think about a parabola, what test is it always going to fail? It's always going to fail the horizontal line test. Again, here's that parabola. I can draw it here. That parabola is always going to fail a horizontal line test. So by restricting the domain, let's see what happens to the graph of that parabola. So we'll start with x equals 0. When I plug in x equals 0, I get 1. So I have a point 0, 1 on f of x. What if I plug in x equals 1? 1 squared is 1, plus 1 is 2. Plot one more point. When we plug in x equals 2, 2 squared is 4, plus 1 is 5. When I restrict the domain, I only have half of my parabola. So now my graph does pass the horizontal line test, which means that when I graph the inverse will be a function. To graph the inverse, I'm just going to take those points and flip their ordered pairs, or flip the coordinates. So if I have 0, 1 on my original function, I'm going to have the point 1, 0 on its inverse. If 1, 2 is on the original function, 2, 1 will be on the inverse. And if I have the point 2, 5 on my original function, I have the point 5, 2 on my inverse. So here is the inverse of that function. Let's talk about the difference between f of x and f inverse in terms of domain and range. Looking at the graph in white, what is the domain of this function? It begins at 0 and goes all the way to infinity. Again, thinking about bounding this graph, I can bound it on the left-hand side, but I can't bound it on the right because it will go on forever. What is the range of my function f of x? Well, if I'm bounding from the bottom of this graph here is at 1, so my range begins at 1, and again is going to go all the way up to positive infinity. Looking at the graph in red, what is the domain of f of x? Again, domain, we're trying to bound from left and right. I can bound it on the left at 1, and then it goes all the way to positive infinity. And the range, my range, I'm looking from the bottom up. So this starts down here at 0, and then it will keep on going up as we follow along this curve. My y values will continue to approach infinity. So my range is going to be from 0 to positive infinity. Look at the relationship between the domain and range of your inverse functions. The domain of f of x is the exact same interval as the range for its inverse. The range of f of x is the exact same interval as the domain of our inverse. So that just reinforces that idea of the relationship between domain and range of inverse functions. Again, guys, I can't tell you how important this concept is. You'll definitely realize it when we get to our last unit, and all of a sudden we start talking about how to find an inverse function by switching x and y and solving for y, and then the idea of the relationship between domain and range. That's going to come back into play a lot. So try to make sure we understand this concept now so that in a couple weeks when we revisit it, it won't be a real shell shock for you guys. We'll see you guys next time. Thanks.